today. It's really my honor to introduce Dr. Kishan Dholakia, who's a professor at the University of St. Andrews, Scotland. I think he knows probably half the faculty here already, and it's really our pleasure to have him join us. As you know, we try to keep the introductions very brief. Dr. Dholakia has had hundreds of publications. He's had patents. He's done IP development. He's done a tremendous amount of teaching, and he is really a real world leader in the photonics world that most of all of you exist in. So really a pleasure to have you come, and thanks so much for coming all the way out to talk with us.
Thank you. Thank you, Matt. And a very great thanks to everybody here for giving me the opportunity to come and visit. It's a real great pleasure to meet old friends, make new friends, and get some sunshine too, which was a little bit hit and miss this morning when I thought I'd brought the Scottish weather with me when the cloud was here this morning. So I'm Kishan Dholakia. I live in Scotland. You can tell from my name and my look, I'm not very Scottish. This isn't the view from my office either, very sadly. This is St Andrews though, so it's a very small town where I live and work, which is, it's only 14,000 people, 8,000 at the university, and this is where the 18-hole version of golf was invented. So if you're into the majors, and I guess with Tiger Woods winning the Masters recently, and then Koepka doing very well, etc., golf is at a resurgence. Anyway, every 5 years or so, we have one of the UK major here. So not this year, but in 2021, all the golf aficionados will come over and try and play the old course here, and that's the Royal and Ancient. And that's a lovely beach we have there as well. For those of you in the audience who know, the Oscar-winning movie Chariots of Fire was filmed actually there. We're about the British Olympic effort in the 1920s. Anyway, a lovely place to visit, a lovely place to bring your family, play golf, and hopefully do a little bit of science too. So what I'm going to do today is I'm going to really tell you a little bit about some of the things I've been doing at St Andrews. Just nature, I've only got an hour. I'm going to whiz through some things quickly and then concentrate to give you a feeling of the breadth that I do, of work that I do. But also I'm going to talk about some of the things where I think imaging could go and give you some surprises. Because that's what you really want. You know, photonics, it's been fantastic. You're here, we're one of the most prestigious institutes that's translating innovations in photonics in the world. But I want to show you some of the things that I've tried to do in a small corner of Scotland that are hopefully getting some attention around the world. If you want to have a look at anything, you can come and find me, ask me, or look at our website. And we're even on Twitter, though for safety reasons, I don't tweet too much, you know, because I'm not really sure what to tweet. But there's guys in the group, and it's actually a fantastic way to get some of our work out to certain communities. So there's St Andrews, and this is what St Andrews looks like. So that's what you're looking at with the golf course, and that's where I live and work here in physics. We have physics laboratories here, and they built a medical building here and right next to me with a bridge so that I don't have to expose myself to the Scottish weather all too often, dragging samples back and forth. But that's made a really big difference to St Andrews, and that's 40 minutes to walk across. So it's a really, really small place, but a very nice place to live and work. Just before I begin, I know people, I need to give disclosures in the US. So the early work on the Airy light sheet microscopy that I'll describe has been commercialized by M-squared lasers in the UK. And some of our optical tweezers work has been, and this is just an example of some of that, has been commercialized by Elliott Scientific also in the UK. So what do I do? Well, actually, I'm a quantum physicist, so I shouldn't even be here. Right? I'm actually a quantum physicist by training, but I've always believed that physics is unified by really exciting principles that can be translated across disciplines. And this is the kind of thing that I've been doing for most of my life. Okay, so at St Andrews, I've developed the first group developing optical tweezers, and this is one of our systems that's commercialized. This is actually my name written in optical traps that's rearranged to work, make the name of Arthur Ashkin. So it turns out my Christian name is an anagram of Arthur Ashkin, one of last year's recipients of the Nobel Prize. Sadly, the Nobel Prize committee weren't dyslexic, otherwise I might have had an inadvertent trip to Stockholm. Anyway, this is actually a very powerful technique, and there's people in the audience here working on this method who've worked on it beautifully. We've done some I'm not going to have time to tell you about all the work we've done. We've done work in biology, but we've also taken work in vacuum, and this is where we actually spun little particles at megahertz, so millions of times per second in vacuum, and did some exquisite physics with that, and that was in the Guinness Book of Records. And also we've done other things with light, including making wave meters that break our understanding, used on speckle. Now, you may know speckle as a way of imaging, but believe it or not, I find speckle as a rich source of information. And that's the whole wave meter there, right in front of you. And that gets you atometer resolution for a wave meter. Now, what am I interested in? I'm not interested in particularly any of these. I'm interested in the top view here, which is shaping light. So I'm actually interested in what light can do. Nearly most people up to now have been used to what this little red spot is, which is a Gaussian light beam, which is a round spot. But I'm interested in it going away from that. In other words, making patterns of light. Very special patterns that can add real value to the world for us, for biomedicine. And I'm not interested just in introducing it in space, but also in time. The time domain has sometimes been overlooked by colleagues in this area. And so that's what I'm going to concentrate on today in this talk. And what I'm particularly going to show is not looking at these innovations of fundamental physics, though I love fundamental physics, and I passionately believe fundamental photonics has to go hand in hand with innovation and translation, which is how we can really shape what we're going to do in the future. But I'm going to show you how we use this for some applications in clinical application and biomedical discovery, perhaps in ways that you might find a little surprising. So what I'm going to do in this talk is talking about shaping light. I'm going to give a short overview of some areas that we're doing, and I won't have time, so apologies to go into detail, but there are things that I think might interest you and will have relevance definitely for the clinical and biomedical discovery. But my main theme is the thing that in photonics we always struggle with, going at depth. Okay, we can do beautiful things with photonics, and you know, when I hold this red laser pointer up, it doesn't go through my finger, but the incredible thing is that without that even, and light just hitting, if you like, the epithelial or the surface, we've still managed to do an incredible amount since the advent of the laser. But imagine we could really go a little bit deeper, double the distance, go 10 times the distance, and still do things. How much more amazing would all the technologies you're doing evolve to? So I'm going to give you a little overview of these techniques here, Raman, holographic microscopy and super resolution, but then I'm going to concentrate on these two things, which is imaging at depth. These are not the only things I'll talk about, and I hope that gives you a flavor of what I think are really the frontiers of photonics and the challenges that we face. So this is where optics fits in the world, in my simple scheme of the world. We've got things like electron microscopy, which allows us to see extremely small things. We've got ultrasound up here, but photonics is an explosion in methodologies. That tells me that my method, thanks, back on track. The photonics has really got a little bit bigger than it should have. It's actually trying to encroach on areas that traditionally have been taken over by other technologies, whether they be electron microscopy or ultrasound. The other thing I want to instill in you is I'm not wedded to one technology. Everything I'm going to show you, what I really like to do, and I believe that the technology should be married to the problem at hand, whether it's label-free, labeled, or whatever. Okay, so that's really, really important, though I do like certain areas because I think they have merit, but that's something that I'm very excited about. Now, why would we want to make photonics go to the super, well, we could maybe displace electron microscopy, we could get to better depths. There's many topics, there may be others in the audience, but one of the big ones, for example, is neuroscience, and also imaging across scales. Can we see centimeters of tissue and then do super resolution at the same time? Maybe we can. How would we do that? How can we do that all with optics to make life easier and simple in a box that sits on your tabletop? So very quickly, some of the methods that we've done, I know there's beautiful work here, for example, with Eric Popmer looking at nonlinear vibrational spectroscopy. We've stuck with standard Raman spectroscopy, and Raman was a rather volatile little figure in Indian history, but an amazing scientist. And of course, he developed this idea of Raman spectroscopy, which you all know, where we shine light and we get the light scattered off. It's inelastically scattered. So what happens is basically the frequencies of vibrations of these molecules get encoded, if you like, onto the light. And from that way, we can actually identify things like lipids, DNA bands, amino acids, etc. And we can get lovely spectra. Now, what innovation did we add? So very simply, if you take a Raman spectra, in photonics, everything comes with everything. So if I shine light on a sample, I'm not just going to get Raman, I'm going to get natural fluorescence as well, for example. Now, you may want that, that's fine. But the problem is Raman's very, very weak. It's extremely weak. Something like 1 in 10 to 6 photons is what you get. So you get these little peaks, if you like, typically on the back of a fluorescence background. So we developed a method which actually just jiggles the laser wavelength back and forth. And when you jiggle it very, very gently, this wavelength modulated one, it's actually different to previous ones mentioned, and I can go into that later if anybody's interested. What it means is that you can remove the fluorescence background without any polynomial fitting. So you don't need a mathematician to do that. What you can do is use your beautiful physics, because as you wiggle the laser wavelength, the Raman shifts. And the background fluorescence stays the same. And then using a simple algorithm, you can get a flat line, perfect zeroed Raman signal with a signal to noise ratio up to a factor of 10 better than you could before. And using this, we've done a number of studies. We've looked, for example, for the first time at the metabolic stage of TB. So mycobacteria, we looked at relapse in TB. And now in TB, which is a very serious disease, and in fact, it's coming back certainly in parts of Europe and other parts of the world where they thought it had gone away. There's actually a correlation between relapse and the mycobacterium and the lipid-rich or lipid-poor status of the cells. And this actually links to their resistance. So we actually did this study here, and then we compared that. This is done in guinea pig tissue and looking at these TB cells, and got very, very good correlation here to that. And this actually links to antibiotic resistance, and we're currently doing some drug studies relating to isoniazid and other things that actually could be used in TB. We used the same idea for the first time, looking at immune cell lines. So this is to make a label-free hemogram. So if you get a blood sample and you look at, for example, the stem cells, we've got basically lymphocytes and granulocytes, you can look at basically all these cell types, CD4, CD8, and also monocytes, etc., and eosinophils and neutrophils, which can be linked also to, which have neutropenia, for example, which is an issue in chemotherapy that can come up. And you look at these cells and they all look the same, but you can use Raman analysis very nicely to get very, very good correlations. So these are the sensitivity and specificity you get. Now, the problem with Raman is always on the tip of an iceberg. It's about to make a bigger impact, but it's always very, very slow. It's very slow. So this is what we did to actually improve that. So even though I'd done Raman for 6 years, we from scratch developed a way to actually cross-correlate Raman with something else, which was much faster. And that was digital holographic microscopy. Basically, it's taking a hologram of a cell. And then what we did was we applied an algorithm used from OCT, and we adapted that to actually then cross-correlate data from that over to the Raman. Now, this time, we're not looking at molecular information. We're just getting morphological and feature information. We want to see how good is that? Is that good enough for us to use? And the answer is yes. So this is our study there where we compared Raman with these holograms. Instead of having tens of seconds to take an image, we could do it in 100 milliseconds to take a beautiful hologram. And we got a very, very nice correlation here with predictions for B cell CD4 monocytes. And then what we did further than that, and I won't have time, is we then developed machine learning and artificial neural network very recently to actually classify these. Now, this is actually something we're now looking at with different NAs to look at high throughput. At the moment, we're getting up to 600-700 cells even in a second that we can get through. And we think this has promise because this is extremely cheap. This uses 100 microwatts of laser power from a simple laser in the visible. So that's something that we thought was very exciting. Now, we also developed on chip work. This picture's not come out well. This is us working at Albert Einstein at New York, looking at hysterectomy, and we developed a nice little chip and we did some urea. But you know, in my view, photonics and science should be out of the box. So here's a little crazy idea that I came up with one evening walking home after seeing an advisory board who were talking to me about broadening science, and this is what we used it for. This little chip, we used it to look at whiskey. So what we did is, now food and drink security is extremely important. So the very same chip you're seeing here, which is 2 pieces of perspex with 2 multi-mode fibers at 90 degrees, is a simple, there's no lenses, okay? And what we did, and I should just run the video now, see? We just take a little drop of whiskey, we put it into the same chip, and then what we do is we just, I apologize for the resolution here for some reason, it's very poor. But you can, for those of you in the front, you can see we can differentiate whiskey for 12, 15, 18-year-old. You can differentiate whiskey that's in a port wine cask or a sherry cask. But the beautiful thing is it shows a sensitivity. Now, in fact, the Raman signal tells you exactly the alcohol content from the ethanol. And it turns out the fluorescence is a marker, and we've done analysis of congeners. So if you go to Scotland, they'll spin you a beautiful romantic story. The whiskey on the West Coast is all peaty, the lowland whiskey is smoother, and you know by eye. But this is very important because counterfeit whiskey is worth £3 billion to the Scottish economy. And there's many people who are wanting to use this. And
take some away. Okay. Can you take some away? You switch out. I think it's into them. We're nearly at the end of the show. So, Dara, you can take that, see if you know what type of whiskey it is. And over here, the computer is going to have a look at this sample I've taken. It's a nice whiskey. We wouldn't like to it. And the computer says it's a pure correct, but a definitely Japanese pure malt. Okay, so let's find out if the computer is right. Am I right? Is the computer right? Yes, it is. There we go.
so that's a famous science communicator in the UK, Dara O'Brien. Some of you know. He's actually an astrophysicist by training. And he phoned me up and said, Kishan, I want your device on my show because I can drink on live TV. And that was one of the most stressful days of my life because we all know having things working on your lab is fine. Taking it with 100 young people jumping up and down, blaring lights and cables everywhere. But we trained somebody in 20 minutes and it worked. And it taught me a lot about translation and making things robust. We have another version of this, and it's not exactly what you see there, obviously, that's ended up in the distillery, but it just shows you how exciting it is. And for me, it was great. I could do this. I could obviously get onto it, and I could buy whiskey legitimately on a research grant. So that was fantastic. So fantastic. And most of it stays behind because we only use 20 microliters. But this is something that I like to embody, things that are really fun, but also have an impact. So many things in photonics can really have an impact both in our food security as well, because sensing is something that photonics is extremely powerful at. We've also done some work in super resolution imaging. I'll come back to this later. Now, I'm sure there's work going on here, and there's many methods. And of course, the Nobel Prize in 2014 in chemistry was awarded to that. And perhaps, though, dare I say it, maybe the methods there are not the ones that we're going to use regularly. We're now finding out other computational, other methods that are proving just as powerful and exciting. But I'm just going to show you one example of what we did in our lab. And this was where we developed and used structured illumination microscopy, which was developed by Mats Gustafsson, as many of you will know, who sadly did not win the Nobel Prize. I believe he sadly died just before the prize was awarded. Otherwise, I'm sure he would have been in the running. But it's actually a very simple and easy way to get at least a factor of 2 improvement in its linear way. So this is, just in case anybody doesn't know, this is my simple way of explaining it. If you take 2 pieces of nylon or put them one over one another, on the lower piece you have a frequency. It's all about recovering spatial frequencies. When you have a numerical aperture, the frequency is twice the NA over lambda. And if I put another one on top, I believe you can see that these large fringes appear, moire fringes. I can count those. If I know what I put on top, and I don't know the one underneath, I can use my understanding of Fourier mathematics to recover the frequency of the one underneath. That's essentially what it does. And this is a little diagram showing how that new information is generated. What did we do? We talked with people at the Albert Einstein Institute in New York who are looking at nephrotic disease. Okay, so when your kidneys stop working and are linked to the blood and low protein in the urine coming out. And what happens there is nephrotic disease is very, very serious and can lead to many conditions. And there, what they were doing was looking at the glomerulus, which are 3 types of cell, and they actually have podocytes which wrap around the capillaries. And what they were doing in that study there was using electron microscopy, transmission electron microscopy, to look at podocyte foot processes. This is the curvature of these things going around there. We did a correlation between electron microscopy and super resolution for the first time, and this day it hasn't come out so well here, but we could actually see the wrapping around. This is immunostaining of the podocyte cells, showing that we could actually identify these foot processes very clearly, allowing a pathologist, Jim Pullman, there to make an assessment. And we're very excited about this. We're so excited, in fact, we have a system that is currently being developed that will go there, hopefully on a more permanent basis, to New York at Einstein to look at the nephrotic disease in more detail. So these advances can displace things that we might not think possible in ways that you might not have ever heard about. So now what I'm going to do is I'm going to move on to the main theme of my talk and go into a little bit more depth of the science, which is imaging at depth, which I think is something that will be one of the biggest themes that we have. So let me start by explaining a little bit in basics about point scanning. So here are 2 cones. These cones represent my Gaussian beam of light focused to a spot. On the left, you see I illuminate with some blue light and I get some green light coming out everywhere. And that's kind of how we do confocal imaging if we have a fluorophore. And then what we do is we say we put a pinhole or some fancy nip-out disc and get our confocal microscope. On the right, you have multiphoton imaging. There's a single photon there. And in multiphoton, you say, let's be a little bit more clever. Let's use 2 photons, because in the world of photonics, 2 infrared photons equals the energy of a blue photon. And what we do is we shine that light down. We're clever because this time only at the focus, where the power density is high enough, will I actually excite any light out? And that's what you see here. However, I would like to contend to you that in both cones, I have light filling the whole cone. I agree here, it's infrared, but I still have light everywhere. And one of the big issues is minimizing the light dosage that you have to samples when you're imaging. And so what's emerged in the last 15 years and is, oops, there we go, that's, oh, I don't know why that's not going to work. I know. Never mind, I'll try and speak louder so I can drown that out. I think it must be something I recorded for some reason it's coming over. So what we have here, oh, oh well, I'm not sure how to stop it. I'm not really sure how to stop that, but anyway, I won't play with it. Let's assume. Okay, so what we have here is, instead of having a point scanning, what we do is we look at 90 degrees. And if we look at 90 degrees here, what we do is we basically illuminate with a sheet, and what we do is we look at 90 degrees in this direction, so we only illuminate. I apologize, I'll have to somehow stop this for a second, see if I can. Oh, there you go. All right, there you go. Apologies. So I'm just going to explain this simply. So why is a sheet of light so important? I'll just sit back and listen to myself. That'll be the easiest way to finish it all, right? Too much technology, that's what happens. What happens here is basically, here you see that if I have point scanning, this is the plane of interest, I'm evenly illuminating either side. If I have a sheet of light, I go through here, but I don't actually illuminate the tissue on either side here. And the beautiful thing is I can, with an SCMOS camera, directly collect the light all in one snapshot. And this is something that's been known 100 years. If you go back to this beautiful paper here by Timo Mappers and colleagues, Zygmundi and Seidentop, they were looking at scattering from Canberry glass. And Zygmundi won the Nobel Prize in Chemistry in 1925, actually saw that. So that was actually the birth of this, but people didn't realize the magic of actually reducing the light dosage. So the light dosage goes down by between something like 10 to 1,000, and it's incredible. So you can actually keep samples alive for days and weeks, and you can actually do some beautiful things. And it's also extremely fast. So these are the 2 things that have really helped light sheet get revolutionized. But the problem with light sheet, there's many problems with light sheet. You might need multiple illumination coming in on this side, is this. So this is a picture I took in Israel of diffraction. Okay, so waves, we know they spread out. And the problem is that when you focus a light beam down tightly, it diverges more quickly. And in the world of physics, we call that the Rayleigh range, pi times the square of the beam waves over the wavelength. The tighter I focus it, the wider it gets on either side. So if I focus on 1 micron, a beam down to a micron at a wavelength of 1 micron, its Rayleigh range will be about 3 microns or something. And that's terrible because it means my sheet is only a sheet here. It's a big blurry sheet over this side. What I really want is a sheet that's like Parma ham. So I can slice the sample beautifully and elegantly. Okay, I can reduce the NA and have a fat sheet like this. I could do that, and then it's uniform all the way through, but the problem is it's thick. It's not like Parma ham, it's more like slabs of cheese. So what I really want is the most beautiful, thin, creating sheet of light. And how do we do that? Now, there are many ways, but what we do is use light beams that seem to disobey the laws of optics. And these are non-diffracting beams. And this makes things very simple. So how do I explain a now I can throw the Helmholtz equation at you. Let me explain to you how light cannot spread without, in just a very simple way. Imagine my 2 arms are light beams. I overlap them. As a physicist, you know you get fringes, interference. And those fringes will be like my fingers here. All right? And I'm standing here with my arms at this angle. Now I walk towards you. You're not too surprised if those fringes don't change. Okay? Now, as I walk toward you, look at the distance between my 2 elbows. It's about 0.5 meter here. As I keep walking to the back of the library here, you can see if I project my elbows back, that cone angle gets bigger and bigger and bigger. It becomes impractical. Now imagine I was a contortionist, and I could rotate my arms in 2 pi. You won't be too surprised if you get a picture like that. That's what a Bessel beam is. The problem is you can't have that going forever, because just like me walking towards you, I'd need a bigger and bigger cone. It would become impractical for the optics that I need. And the problem is also that the light is distributed in all these rings. In fact, whenever you see a Bessel beam, you should ask a lot of questions, including the fact it's not really non-diffracting, but the fact is that the light is distributed. So only, if you have a Bessel beam with 10 rings, 10% of the light is in the middle. So that's terrible. So this is how you might make it in the lab. But the beautiful thing is what happens when you do multi-photon with a Bessel. So here's a picture we took in 2008, single photon microscopy, multi-photon, and multi-photon with a Bessel beam. It's a single line. But hold on a moment, I just told you it had all these rings and I threw 90% or something of the power away. What happened? Well, look at this table that we drew here. This tells you that if you use single photon excitation, the first ring would give you 16% of the energy in this one of that, okay? But if I use multi-photon, because I have this quadratic dependence, the side lobes don't matter. Pattern beams are fine. And in fact, in the second harmonic, only 2.6% actually matters. So these side lobes completely disappear. Now, what Eric Betzig did, in fact, we wrote a grant at the same time, but the UK EPSRC didn't give it to me for about 1.5 years, but anyway, at that time, but is he uses patterns of these next to each other to get around this. Because if you can't always use multi-photon, in single photon, you have to use what's called lattice, so you use arrays of these, and that suppresses the side lobes. But you know you can do a little better. You can do a little better for certain applications. And that is what this beam is here. This is the Airy beam, the same Sir George Airy, the British astronomer, and the Airy function you have in your microscope objective. This is the same. This beam also propagates, and it doesn't change, just like the Bessel, but it does something funny. It goes like this, in a parabola towards you. Looks very crazy, and it's graded great numbers of papers for fundamental physicists in OSA journals. But it's very, very useful. This beam is asymmetric, okay, and that's extremely important. Okay, so we're going to now find out what that means. And this is the beam. So I call this the banana light sheet. So we have a beam. It looks like the most ridiculous light sheet you'd ever made. It's actually much easier to make this beam. We make it with a simple piece of glass, and we scan out one direction. And that's the beam there. There's the main core stick, which is this. And these are all the rays that actually make that core stick. And we scan it up and down. Okay? And this beam, if you're interested, came out of the Schrödinger equation, analog of quantum physics. So Michael Berry and Balzas, in probably the most highly cited American Journal of Physics teaching paper in 1979, said a dispersion-free solution to the Schrödinger equation was the Airy function. And then the group in Creo here made it in the optical domain. And that's our work in trapping. But this is what we do then. And then what we do is we scan through a sample. Now, it gives you a beautiful comet tail. Now, let me just, for time, I won't go into all the details, but the beautiful thing is all the lobes help me. I need a mathematical way to recover it. But the beautiful thing is, if you look at what's called the optical transfer function, because of this asymmetry, the real and imaginary parts of the beam go to 0 at different times. So some part of that beam helps me recover the image always. And what really happens if you do a comparison is you get this. That's a Gaussian beam. This is a Bessel beam. This is another Bessel beam that goes further. So that number next to the Bessel tells me, if you like, how far down the room I walk, like with my arms. And this is the Airy beam. It gave me a factor of 10. Like a good physicist, I started with fluorescent beads in agarose. All right, and I got a factor of 10. Okay, all good, and all the graphs look good with the field of view, etc. But that's not really what you want. And now I'm not going to show you any pictures we've taken. This is translated since then and is now a product for this company here and is in 15 labs, including 2 in California. And these are all data taken by other people. I think the best way to sell your product is give it to the hands of other people and let them take data and show you what they can do. So I don't have all the details of the objectives or the sample prep here, but these are some of the examples of what people have done. This is in London. Here, this is a cleared mouse brain. And this other one's nice too, let's see. And this is commercialized here, and they employ quite a few people in Guildford, Surrey, about 12 people, and it was did very well, winning an innovation award. But what I want to convey to you is that something very surprising in quantum physics can go to imaging and within a few years make a product that's really, really useful. Now, there are many variants of this now that we have on the go, and I'm going to show you some of the latest innovations. But you can see the level of detail we can get using this. Now, I must point out that the Airy beam, because of those lobes, we need a process called deconvolution, which is basically a Wiener filter and using a mathematical process to recover the image. But we can do that now extremely quickly. It's not the beam for every sample, but it's extremely exciting for many samples, and you'll see some of clinical relevance in a moment. So there we go. And this is some latest work looking at a gut organoid from a mouse. This is again taken in the Karolinska Institute in Sweden. So I'm gobsmacked. The first time I saw these pictures, I said, guys, why can't we take these pictures at St. Andrews? And then I thought, well, it's okay, we're not here to take those pictures. It's great for other people to improve, optimize the apparatus, take the data and show us what it can do as well. So this is part of the program that we can actually do. So these are Paneth cells, stem cells, and also looking at nuclei in data that we can actually see. We'll just wait for it to zoom in, maybe, if it is. Maybe not. It's amazing what you can do with data. You just spend hours watching it, not knowing what it means. But I just love the detail that you can see when you zoom in on this. So one of the things that interests me is how much resolution you can get. You can see the immense resolution we can get in this, as well as the large field of view, which is extremely exciting for what we can actually do. So this is there. But what really might interest me is taking this towards something that might surprise you. Histopathology. So we've been using Raman and also DHM as well for histopathology, but I've been interested in that. And credit must go to Jonathan Liu, who's was definitely ahead of us in this here with this beautiful paper that he did in 2017 at the University of Washington. Now in histopathology, with 1.7 cancer diagnoses in the US, people are actually using things such as structured illumination or MUSE, which actually uses UV irradiation. Now this is fine, but what can light sheet offer? Light sheet is extremely fast, it's extremely cheap, and it offers 3D volumes. So the first thing we did is, well, I won't go into the optics of this, but it's a very simple variation, which is we basically made a variant of this microscope that he has, and this is the kind of resolution that you can get. And so here what we did was we've developed collaborations with the University of Edinburgh Pathology, Imperial College as well, with 2 London hospitals, Charing Cross and King's College, and actually looking at that. So we looked at rectum tissue and cancerous tissue and got some very nice pictures. Now the problem was, if you look at this paper, it's excellent, but there's a few limitations which I've just listed here. So we started to think how we could attack those limitations. And so I'm going to show you stuff that's not published and new from our group. So this is now the first light sheet that actually uses both Gaussian and Airy in a compact geometry, and also with both beam modes. And also in the next slide, you'll see we've added super resolution. Now you're going to ask how I did that, so I'll leave that for the next slide. So this is imaging at scale. So here what we're doing is looking at Gaussian versus Airy. So this is with breast tissue, which can be very hard to actually get good pathology samples. You can see the Gaussian beam clarity is very poor, but the Airy beam, as we might expect, gives you excellent imaging right across the whole field of view. Now these are all usually acridine orange and then rinsed in PBS or acafladovin. And here what we also have is the Airy beam versus the Gaussian at depth. You can see the variation we get in the Gaussian, whereas the Airy gives us much better structure into the structure that we have. And again, we did the same here, getting quite good resolution over a large field of view. And then we went one step further. Now, super resolution is tough. So we did it all computationally. So what we did was there's this beautiful and not widely used enough algorithm developed in University College London, used for STORM by Enrique's group. And what they do is, I won't go into all the details, but they look at sparse images and they say, if you have a Gaussian, what we do is we look at the radial symmetry of the object and we take multiple images to look at gradients. And what they do then is they use an algorithm to collapse the beam down, that PSF. And so they can go from this to this. We have applied this beautifully just with a camera. There's no additional optics onto our light sheet, and you can see the advantages already here. We're aiming to have a light sheet that will be able to do centimeter squared with hundreds of nanometer resolution in the not very distant future. So that's a work in progress, and we'll be going to our colleagues in Albert Einstein actually in about 2 months' time. We've also been working, not only at that, we've been listening a lot to biologists looking at cardiovascular and other diseases, looking at innovations in sample mounting. If you look at a light sheet, nearly everybody will mount samples, for example, in things like agarose. So here, for example, we have Drosophila flies. So there's model organisms like Drosophila, C. elegans, zebrafish. And this is fine, and you can do that, and you can see this, and this is something old. But what I wanted to do was do something that people would surprise people and do something new. So this is what we did earlier this year. And this is where we developed the first all sound-based imaging of mounting of a sample. The sample isn't in agarose, it's in this native medium. So this is a 2 to 5 day old zebrafish just held by sound waves. Now I know optical waves is what you might be interested in, but optical tweezers are very weak. They're very weak. They only give you piconewton forces. That's kind of the gravitational force of attraction between you and your pizza slice. But acoustic waves, not very well known, can also do beautiful. That's a zebrafish there held between 2 transducers. So we developed a very beautiful little module that can fit onto any microscope, and we have IP around this. And here what we did for the first time was actually looked at zebrafish, and we actually added drugs. So here we have looking at verapamil and noprophene, and actually looked at the change in the heart rate and monitored that as we slowed and raised the heartbeat. And on top of that, we developed a beautiful new optical flow analysis algorithm that looks at the stress and the strain on the heart. Now, I understand in cardiovascular research, this is very exciting. And there's also many, many embryos that people don't want to actually embed in our agarose. And also you've got the chorion, if you like, the fertility envelope in many embryos, and we can actually study that now in a way that could not be studied before. So we're very excited, and we've got people wanting to work with us on this new technology too. So these are some of the breakthroughs that we've seen. This is not our work, this is work at Philip Ahrens and Philip Keller in Lightsheet, and we've got also super resolution. But what we'd really like to do is change slide. Really like to do, he says. So there you go. Is go deeper. All right. So we've got light sheet that goes reasonably deep. Maybe the Airy beam helps. But you know, light scattering, what stops us taking images at depth? But I want to do it in a simple way. You talk to a physicist, and you know the first thing they'll say is, let's do adaptive optics. Let's buy a spatial light modulator. Let's put on fancy polynomials. Let's do some maths. Let's correct aberrations. I'm now going to show you not one, not two, but 3 ways we can do it without doing any of that. So let's go to the first one. Oops. So the Beer-Lambert law, this tells us, it probably should be called the Bouguer-Lambert-Beer law probably, and Lambert's very interesting. He was the first mathematician to prove pi was an irrational number. And it's a pretty clever thing to do. I have no idea how he did that, but anyway, there you go, fantastically important. But what we know is we have this exponential decay if you put light in through a sample. And so I was wondering, you know, if you take a sample and let's say, I have no idea about the aberrations, but I know light's going to be degraded and probably exponentially decay as well as it goes through. How can I recover signals at depth easily that everybody in light sheet could do? Let's just start with that. It can be applied to this can be applied to OCT, it can be applied to other ways. And I remembered a paper we did 10 years ago in Optics Express, very simple, and it was something that nobody in these beams ever tells you. They all tell you about the beautiful transverse profile, and I told you about that, but I never told you what the intensity was of those fringes as I walked across to the end of the room. Believe it or not, that intensity does this, something like that. So they're cheating. In fact, it fluctuates. But what we found was a mathematical way to play with the input pupil function, to tailor it off, to get it to rise, or to make it go down. And this we called attenuation compensation. And then we've just applied it to an Airy beam. So here's an Airy beam, and I'll just show you how that works. So there's an Airy beam there, and there's my input plane. And what we do is we say there's a nice curvy Airy beam, which might be my light sheet. Now, I know in my sample, the light's going to be pretty bad here because it's gone through a lot of the sample. Okay? But the beam is very nice, it's non-diffracting, it should keep its shape. So what I can do is I can do something very basic and very naive without any aberration correction, which is I can just weight the beam to have more intensity here or here. So if you like, the rays on one side of the pupil contribute to the depth in the sample, the rays on the left early in the sample. It's really simple. And you can just do it actually with a simple neutral density filter. And then what we did was we did this. And here, for example, we have kisspeptin neurons in the mouse brain. And here we have our colleague Javier Teller, who's looking at reproduction. And he was looking at counting dendritic spines. Look how simple that is. Light sheet, you can't do point correction. You've got a wide field of view. How do I do that? Here we managed to do that over a very large field of view. And we can get improvements up to 150%. And here you can see a structure in this little structure called lamella opercula. And here you can see, again, the CNR ratio increased. How simple is that? This can be applied to Bessel, lattice, any light sheet in the world. Now, there are some nuances if you apply it to some of them because of the way the attenuation compensation is applied. But look at the depth penetration that you get here in that sample. So let me tell you about some of the things that I think are really going to revolutionize photonics. There's something that we already know, but is coming up, and you may have heard snippets, but I would contend this is something that's been slightly overlooked, which is three-photon microscopy. Multi-photon is good, three-photon is amazing, and its time is now. This is because there's a convergence of need, excellent advances in lasers, and also our understanding of shaping light. This work must be credited to Chris Su's group, who's done beautiful things. Some of you have seen that. This is 1700, going deeper into the mouse brain. What are we doing here? So instead of using 2, we use 3 photons. And so we go to a longer wavelength, and that means our scattering goes down. This is a scattering graph here for a tissue model, but for the mouse brain. And you can work, for example, at 1300, also 1700. Obviously, you've got to match to the fluorophore and that your cascade of photons actually excite things. So 3-photon is coming, but what can we do that's new? So here, last year we developed the world's first ever 3-photon light sheet. So here we have, for example, a cell spheroid, a cancer, and here all I'm going to do is show you the input side of the cell spheroid and the other side. This is just showing you on fluorescent spheres that we get our factor of exponent of 3, and then we did some CNR studies to show you on this side, it's 2-photon and 3-photon give you about the same. On the other side, 3-photon looks a lot better. If you don't believe me, let's have a look at the video. So this is just a simple Gaussian light sheet through a cell spheroid. For now, I can see both sides of it very, very easily in 3-photon. Now, this is not the best laser. So this sample didn't survive very long, but you can see the physics is beautiful. All right, so that shows you the cell spheroid, and we can see both sides with one objective. Then what we did is we did a numerical model and understood how the Bessel beam would do better. So that's that beautiful beam that goes deeper. But now I'm going to combine that with the 3-photon. And look at this. This is one of my favorite pictures we've taken in the last 10 years in the group. These beads. But you see these little blue blobs on either side? That's that 2.6% on that table. That gives you artifacts. We can remove it completely. And there you can see that, for example, with 3-photon, the side lobes completely wash away. And how good is it? If you look at the excitation order, the resolution, even though you go to a longer wavelength, stays about the same, and then the field of view increases tremendously. So that's what we've done here. So that was, and it was only Ashkin's Nobel Prize winning paper, knocked us off top spot there, but it was very, very exciting. And now we have just bought a very nice 3-photon laser, and so we hope to have the widest field of view light sheet microscope in the world within the next 3 months with high resolution. And I think there's no aberration correction here. And these lasers are getting smaller. I'm talking with this company, Coherent, about developing a single box unit that will actually develop this into a new product. So now let me tell you about my craziest idea in the last 5 years to end off things. So which is not just looking in space, but looking in time. I'm okay for time, am I? Terrific. Okay, so this is something that I've been wondering, how do we go through something very, very easily? So if I want to see this, and I want to see it under some tissue, that's going to be really, really hard, an embedded object. So let me tell you about something that's not talked about enough. So this can be applied to 2 or 3-photon. When we do multi-photon microscopy, normally what we do is we focus in space. I take a lens and I focus the beam down and get a spot. You don't have to focus in space. You can focus in time. The pulse has a short duration. So if you look at the half the Nobel Prize last year for Donna Strickland and Gerard Mourou, they got it for what's called chirp pulse amplification. So what they did, they took a little pulse and said, I want to make it a stronger pulse. Oh, I can't do that because I'm going to blow up all the optics on the way. So what I'll do is I'll stretch the pulse out in time, chug it up in energy a little bit, and then compress it back again. And it'll be nice and big and peaked. Now that idea has actually also been used in the time domain for multi-photon. So here, instead of focusing in time, what you do, in space, you focus in time. How do you focus something in time? That doesn't make any sense at all. Well, what you do is you take the colors, this little pulse, and you spread it on a grating. You spread the colors out, and they come back to a small spot. There they are. And that, only at that plane there, does the pulse have the same duration. Everywhere else, it's nice and flat and stretched out. And this is temporal focusing. Apologies, I should have put the 2 references on here. But of course, Yaron Silverberg and Chris Zhu's group saw this in 2005. But there's something magical about this that most people had missed, which is if you look at space, we've got to do aberration correction. But if you focus in time, this is robust to scattering. That sounds impossible. Why is that? Well, here's a little model that we did. And basically, this is a beam, and it goes through 900 microns, nearly a millimeter of tissue, and it stays the same. Here's another non-temporally focused beam, and it gets blurred due to speckle, as we already know. And this is already known. And one way to think about it is the model is a little bit more complex, but for today, think of it like survival of the fittest. All these photons come in and they're all going all over the place. But some of them are ballistic and they all make it to the back of the tissue. All right, so long as I have ballistic photons and they get there, and they're the only ones that contribute to my little pulse. Everything else is kind of lost. So they're the only ones that help. It's actually really simple. All I need to do is put a grating in front of something. Is that true? Well, some major groups do think so. These are 2 beautiful papers. This is one by Valentin Emiliani's group, who are leading the way with neuronal access. And they're doing temporal focusing. Here we go. Over through 250 microns of brain slice. You know what they did? They said, oh, I know the shape of the neuron. I'm going to stick the neuron under the tissue, and then I'm going to temporally focus a beam down. They knew the shape of it. They used this spreading in time and made the pattern of the light above the tissue what they wanted. And look, it works. There we go. It's brilliant. Peter So and Ed Boyden's group did exactly the same. But what's the problem with what I've just said? It's not imaging, because I already knew the shape of this. If I put this under tissue and then I image a beam onto it and I know the shape of this remote control, that's not much fun, is it? What I really want to do is recover this image. I want to stick this under the tissue and get it shaped before I do that. How can I do that? This is how you do it. Use something that is not used hardly in biomedicine called single pixel detection. Did you know the way you can take an image can be reversed? Instead of taking a picture and putting it onto a nice CCD array, what I can do is, and it sounds absolutely daft, is I can take this and I can image patterns onto it. Funny chessboard patterns. And each pattern reflects off here, and then let's say my eye goes click with a little detector. That click multiplied by the pattern over time will give me this shape, right? So what I do is I make patterns, I shine them on the face, and this goes click. Every time that goes click, I multiply that click by that pattern, and I do that. So here's a smiley face, that's pattern 1, that's pattern 2, pattern 3. You might say this is a ridiculous way to make an image. It is, because in the visible we don't need it. But let's say you don't have a 2D array. Let's go to the near infrared or something. That's exciting. That's very exciting. So what do you do then? So what we did was we used this temporal focusing to actually project patterns in simple chessboard patterns. You can just download them in 5 minutes through the tissue. These modulated patterns. And what we did is we just collected the backscatter light coming back, and this goes click. And every click there, multiplied by every pattern that I project, allows me to recover this with no a priori knowledge of anything. So for the first time, I've imaged through scattering media without ever knowing anything about the medium or doing any correction. Does it work? Yes, it does. So this is my hidden object. Physicists love making funny smiley faces in their clean room. There's my normal microscopy, and that's the retrieved image I get through 200, 400 microns. Now, at the moment, we're speeding this up. I won't have time to go into this, but we're using compressive sensing as well to reduce the number of patterns below the Nyquist limit to do that. And we can retrieve cells below tissue. So there's what we should have seen, and that's what we see. So this is really, I think, going to set the agenda. This is for the first time you can go through tissue, higher numbers of attenuation lengths than you could with normal multi-photon, but with no a priori knowledge. Now, of course, you could combine it with all the more fancy optics, but this is a simple modification to a multi-photon microscope. So I'm going to stop there. Of course, this is done with a wonderful team of people. So that's a snapshot of my group a couple of months ago. I just want to highlight some of the excellent people I've worked with. So Tom Vedenberg and Jonathan Nilk here for the Airy light sheet. Stella's doing the pathology work. Federico, Adria, and Philip have worked on Three-Photon and also the traffics method that I mentioned. These are my collaborators who've provided samples. I particularly want to highlight these 3 collaborative places that we've worked with, which is Mike Prystowski and Jim Pullman at Einstein, who are working with us both on the histopathology work and light sheet. Hamlin Center, who provided fresh tissue samples for breast and colon, and Simon Harrington fixed samples for breast, and David Lyons, who supplied us a lot with the zebrafish for our acoustic light sheet. So I'd like to stop there and thank you all for your very kind attention.
So your compressive sensing scheme has this nice zero background and this nice smiling face. Usually one of the weaknesses of compressive sensing is if you have a background and a signal on top of the background. How robust is your method for that?
Yeah, so the answer is I don't know. As we've got a little bit of time, let me indulge you and just show you. I didn't really show the compressive sensing slide. So this is an example. This is the same way JPEG, if you like, compresses our pictures with these wavelets. So what we've just done, I'll skip through this. This is an example of how robust it is. The nice thing is the temporal focusing helps in discrimination of light either side. So this is a compression of only 6% of the light, and we can still see with this optimum pattern, which is a wavelet combined with noise, you can still get an image.
But you still have zero background. So usually if you have
Yeah. Oh, I see. Again, this is new work. We haven't done a detailed study on it. Yeah, okay.
Everything up.
Yeah, short note. Okay. I don't know today because this is work from about 3 weeks ago that we've done, but it's looking interesting and worth pursuing. But you're right, we do need to do a lot more studies on that.
The Three-Photon light sheet is very, very interesting. You probably need a lot of power to get a Three-Photon fluorescence, right? So how does it affect the...
Excellent question. Right, so for Three-Photon, that paper was done with the wrong laser. So we had the physics right, but we didn't have our correct laser that could go to 1300 and 1700. So for that, I completely agree. It was, the rep rate was too high, the wavelengths were wrong, etc., and the samples only lasted 10 minutes. If you look at Chris Zhu's work, for example, he's managed to show that the viability of samples, and he's done live mouse brain imaging with Three-Photon, is absolutely fine. So you can keep the rep rate quite low and get the average power low. It's absolutely fine at 1300, and he's done work at 1700. So we're extremely, we've done some calculations on that, and so we're very excited that our light sheet will be equally as good. We've also got some other strategies. We've got a scheme potentially to use compressive sensing as well on the imaging side to reduce the power. So this, I can't say today because we only got that laser 10 days ago, and the guys are still just aligning it. But I'm reasonably confident that we will have a very exciting light sheet with that, with no damage to the sample.
I've never seen the holding zebrafish acoustically.
How?
How stable is it? Do you need to shake the wavefronts to keep it stable, or how big is zebrafish?
Right, so these are excellent questions. So let's start with how big is zebrafish. So for ethics reasons, we can't go over about 5 days. But if we had the ethics approval, we could probably go to more adult versions of zebrafish. How stable is it? We don't shape it. It's just a simple standing wave. We've done some studies on motion analysis, and that zebrafish heart rate would not have been able, we wouldn't have been able to monitor that. So we've actually limited it to about a few nanometers even motion. So it's extremely good and stable because it's quite heavy, it's big. And so it just sits there. Now, if you wanted to do a fancier acoustic trap, please go ahead. We're novices in it, but the real magic there was the application, the combination with light sheet, and the simplicity. It's just 2 transducers in a box. And we've had lots of people in biology wanting, developmental biology as well as zebrafish, wanting to work with us on that. Yeah, so that's an excellent point. So let me just come on to that. We don't spin it here, but either with an optical beam, or we could add with other transducers, with a phased array, for example, we could do tomography and rotate the sample. We've not gone that far because what we're waiting for is the right biological question. So that was what we wanted to do there. There we went a little further with the heart rate, but you're absolutely right. You could do more things with that.
Just to follow up on this question, what's the viability of the zebrafish embryo after this kind of?
So we.
And can you work with pairs of acoustic tweezers to manipulate things within that?
Excellent question. Okay, so let me answer the first one. We've done viability studies holding the zebrafish for a day and a half, and it seems to be fine. We've looked at assays on them. I'm not saying that's as robust as maybe you would like, or maybe in a long study, but it's extremely good. Acoustic traps have been used in other samples, and they seem to be no worse than certainly optical traps if you get things right. And so I'm reasonably confident it will be useful. You're talking about multiple traps. Right, so this is a standing wave trap, but what you can do is you can design single acoustic traps. So basically these are different arrays where you focus the sound here and you can hold samples here. Now we haven't designed that because we don't, but if you wanted to put 2 zebrafish next to each other, you could do it in this trap because of the standing nose, but you'd be because it's a standing wave, you'd be fixed to the half the wavelength there, okay, which might not be the spacing that you want, but you could design 2 transducer arrays for single acoustic levitation if you wished, but we haven't done that.
Solution is better to have high resolution, high intensity. But at the end of the resolution, you get some morphology, some shapes, show. But that is not entire information.
No.
So is that the method you're using, the method to obtain this very high resolution, actually incompatible with other methods, for example, spectral
No. That's a very good question. Yeah. Okay. So let me, if I just may go back to something I just said earlier, just to exemplify your point. So here, for example, we did Raman with holographic micro. So okay. Yeah, so I think you're asking multimodality, whether we need resolution. Do we need really high resolution? Well, the answer is, well, I would say certainly for things like the nephrotic disease, yes, we do, but we don't need multimodality. For this, do we need it? Not necessarily. Here, in the DHM, the resolution that I need, we're currently doing a study on this, is to say, Raman can pick out, if you like, different cells. Let's say it can pick out CD4, CD8, NK cells. DHM doesn't pick out molecular information, but there's a slight granularity difference. And then we had an OCT algorithm. And then the question is, how much of this do we need to actually see that? So you're right, we need to think about what the resolution is that we actually need. But you're right, if we took a large area, we wouldn't get the granularity and we wouldn't get the resolution that we could differentiate it. So we're actually doing a study at the moment on what is the maximum NA that we can use to differentiate different types of the immune cell subset and still get a classification that is compatible with Raman. Now, it may not be, some cells, for example, B cells are quite difficult to distinguish from CD4s. It may not be that we can actually get a very wide field of view for the reason that you say.
Same question.
Yes.
I'm surprised to report it.
It does. How do I get high resolution? No.
It's how you get the physiology out.
Yeah.
So you're looking for solution.
I understand. How do you get a physiological information out? So that is a very good question. At the moment, everything I've shown is labeling. Of course, we can do autofluorescence potentially. So the Traffics method, the method I showed at the end, can still pick out endogenous markers such as NDH, but we haven't gone that far. I completely accept that point. It's early stage for that work, but the potential is there. That method is not just label-free, it can go through endogenous fluorophores as well. But you're right, it's a valid criticism at this stage of that work.
For your time focus technique at the end, how deep do you think you can go, and can you scan it deep?
Right, so let me, with temporal focusing, let me answer how deep we can, how we scan in Z. What you do is you have a temporally focused plane. So what you do is you have something like electrically tunable lens, for example, that takes different slices. Okay, so that's how we can make, for example, a 3D composite picture if we wanted to. And each plane is decided by the pulse duration, because the pulse duration there then dictates how thin that is. Now, obviously you'll have issues of dispersion and a few other things that may cause some issues. How deep can we go? We're now setting up with the 3-photon laser that you saw, a 3-photon version of that. We hope to go up to nearly 2 millimeters. That's what preliminary calculations show through a mouse brain. Now, we hope to quantify this. We also want to do it for histopathology and cancer as well, but that's the numbers that we've got on the model. Whether they come out in practice, we don't know. The 3-photon laser, we've got so many experiments to do. I've only got 2 guys in the lab, so we're going to start with the light sheet first, and then we're going to go to this traffic system to go deeper. But so it's a work in progress, but we're hoping to get up to a couple of millimeters.
Okay, well, thank you.
Yeah, that's it. Hi.
We will have a.
Yes, I know. I'm looking forward to it. So look forward to speaking to you later.
So we do in deep imaging.